Hey, good morning. I'm Paige Browning. It's Monday. This is Seattle Now. Opening the light rail across Lake Washington over the weekend was an historic moment. Trains go across bridges regularly, but never before has there been a train over a floating bridge. Engineers worked on the challenge for years. In a minute, we'll hear why it's so complicated and how engineers pulled it off. But first, let's get you caught up. Seattle Mayor Katie Wilson's plan to rapidly expand shelter beds is before the city council today. She wants to use nearly $5 million in unspent funds to provide more emergency shelter space. She also wants to raise the cap on how many people can live in a tiny house village from 100 to 150. A council committee will hear the idea at 9:30 this morning. The Seattle Convention Center finally turned a profit last year for the first time since 2019. The Puget Sound Business Journal reports it took in about $1.4 million in 2025, a few years after its major expansion in downtown Seattle. The Convention Center CEO told the paper their profitability is due to a significant pickup in in-person gatherings. The Convention Center suffered years of losses after the pandemic took a major toll on conventions and events. And a note from our team, KUOW's spring fundraising drive wrapped up over the weekend. Thank you to everyone who made a donation to Seattle Now. With your support, we bring you shows twice a weekday and on Saturday, too. If you haven't had the chance to donate yet, you can still do that. Click the link in the show notes. Every gift really makes a difference. Thank you from the Seattle Now team. We'll be back with more headlines on tonight's episode. At long last, Seattle and the East Side are connected by light rail. It's a huge moment for the region.
It has been the work of several generations of leaders to go from the promise we made the voters in 2008 to delivering on that promise in 2026.
That's Sound Transit CEO Dow Constantine speaking at last week's media preview of the light rail connection across Lake Washington. This will be transformative for everyone who travels in and around our region. On top of the time, money, and political will it took to get here, making this cross-lake connection by light rail was a huge engineering challenge. Trains have crossed bridges before, but getting a train across a floating bridge is an historic moment. It's never been done before now. Washington State started the process with a list of 26 problems engineers would have to solve before making the train a reality. Several of those problems revolved around movement, according to Sound Transit Deputy Chief Engineer Brian Holloway. Floating bridges are not as stationary as other types of bridges.
There's actually three types of movement. The bridge can go up and down to the water levels. It can go side to side with the wind and wave action. And it can actually twist as well, especially as cars and loads and other things can happen.
Another challenge floating bridges present is they're basically a giant boat.
And if you've ever been in a boat, you know that you want to sort of stay in the center of the boat. If everyone starts to go to one side, the boat will start to list a little bit to one side or the other. So we have to take that into account as well.
Because light rail tracks and the train are on one side of the bridge, balancing its weight was a challenge. The biggest challenge was figuring out how to get a light rail train to transition from land, where there isn't movement underneath the train, onto the floating, moving bridge. For a car, a transition that sways and rises and falls with the water isn't a big deal.
For a car driving with pneumatic tires, you're not going to see these transitions.
Okay.
And the only thing that you might notice is as you drive over the bridge, you might hear a ka-thunk, ka-thunk.
Oh, yeah. When you're kind of going over those connections.
For a train, that sharp change in geometry is quite problematic.
Professor Travis Thonstad worked on that problem in the early days of design and testing. He's in the University of Washington's Department of Civil and Environmental Engineering, and now he monitors the bridge and the train's operation. But back when he first worked on the project, he was a master's student, and he's here to help us understand the puzzle of making a train float. Hey, Travis, thanks so much for coming in.
Thank you so much for having me.
So Why do we have a floating bridge in the first place? Let's start there.
Yeah, so Lake Washington poses some unique challenges. The lake itself is sufficiently deep, and the underlying soil is sufficiently poor that a fixed-span bridge, like a suspension bridge, like the Golden Gate Bridge.
Where you just put some posts down and call it good?
Exactly. So the cost of that kind of structure for Lake Washington is prohibitive. And so they needed another solution. And a gentleman by the name of Homer Hadley, for which one of our floating bridges is named, had the idea to put concrete pontoons across the bridge. At the time, they thought this was a horrible idea, as one would, and they called it Hadley's Folly. But later on, this idea gained traction, and they built the first floating bridge over Lake Washington, and that finally connected Mercer Island with Seattle.
So now the task for engineers became put a light rail over Interstate 90, over this floating bridge as part of the Sound Transit expansion that voters had approved and all of these government bodies had approved. This is no small job.
That's right.
So then there's a big team. You're involved with this big multi-agency team charged with designing and building this out. On this team was Sound Transit, consulting firms, construction companies, even the Bellevue City Council to weigh in on some of the approvals. How did the team get started? Doing something that's never been done before in the world.
In 2011, there was a team put together on a contract to look at specifically the expansion joint for the train. They had an idea back from the 80s.
Okay.
And they were thinking this might be the right thing. A guy by the name of Andy Fone out of the UK, who was a special track works engineer, brought out this idea. And he had dreamed this idea up. And when it was explained to the engineers, their jaws hit the floor because it was so beautiful and simple. He cut a coffee cup in half. He had used the stir straws and then supported what are popsicle stick rails over it. There's two spans. One would be our floating span, for example, and one would be the transition span. And he's actuating those and bending them like you'd see on the lake. And in between were these two pieces that he had devised. It allowed full support over the joint, but also forced the rail into a smooth curve that you could design so that you could pass that point at any speed, all the way up to 55 miles an hour.
So there's this big team. They come together. They start to figure out, here's how we might be able to build rail tracks over a floating bridge. How do you test this thing? You can't exactly test it over the I-90 bridge, which is in operation, right?
None of this happened in a vacuum. So for everything that we are talking about in terms of all the engineering challenges and all the solutions that had to be dreamed up, due to the unprecedented nature of this project, there's a lot of testing that had to be done. And the track bridge was one of them. We did testing at the University of Washington on a portion of it. Then they built a prototype in Tacoma at a place called Jesse Engineering, and there was testing done at Jesse Engineering to make sure that it was moving in the way that everyone thought it should. And then they shipped the whole prototype and a Sound Transit light rail vehicle out to Pueblo, Colorado, to the Transportation Technology Center. And so it's this huge test track. It just looks like a train set, but full size.
Why?
So they have a very specialized facility in Colorado, the Transportation Technology Center, and it's basically like a train set brought to life. So it's a full-size train set, and they do a lot of work for the rail industry to look at safety, to look at different systems. And they simulated what the bridge would look like. So they actually had some changes in alignment that they did to the track bridges to simulate what they would see on the bridge.
And did it work?
And it worked beautifully, yes, which is comforting. But we still learned a lot about the stiffness of the system and some of the different components, how to do maintenance on the different pieces. So there was a lot that was learned out there as well that informed what is on the bridge today.
Okay.
Yeah.
So now you have a working model. Can you just in simple terms tell me, how does this work? What did the team develop to get a massive train over a floating bridge?
There are a few other technical challenges there as well. One of them was how to attach the rails to the bridge itself. If you imagine you're trying to put rails onto a floating bridge, probably the easiest way you could think to do it is to just nail everything down or bolt everything in.
Yeah, like you see on the ground.
Yeah. Well, you can imagine that for a boat, for a floating structure, you don't necessarily want to be drilling lots of holes into the deck.
That could leave room for water.
That's right. So there's a lot of steel that you have to avoid while you do it because it's an existing structure. So that poses a challenge. You don't want to weaken the structure. And then you imagine putting a lot of holes all in one line because rails are straight. And it's just like the perforations on a piece of paper, right?
Oh, yeah. That could just be ripped apart.
So there's a plane of weakness there that you create. So
how do you stick these things to the bridge?
So you use a very special kind of glue.
They're glued.
And so not only is this the first time that tracks are on a floating bridge, but yes, all of the railroad ties are glued down to the bridge. And it's a special glue. It's called Dex G.
Okay.
Probably not that important.
I like it. Dex G. That's what you're riding on.
That's what
what's
you're riding
connecting
on.
you to the bridge.
But there's also a very interesting material between the Dex G and the railroad ties, a squishy material called cork-elast.
Is this cork made?
It's a
cork
mixture
product?
of cork and a polymer, yes.
So it's the bridge deck,
Bridge
cement
deck.
or
Yep,
concrete.
Yep, concrete, yep.
And then basically a cork structure to give some flexibility.
That's right.
And then super glue
Yes.
and
yep.
railroad tracks.
And railroad ties. Yeah, and the ties themselves are also very unique because they had to be super lightweight because one of the issues with putting this system on the bridge is weight.
How did you account for the massive weight of the train?
There was a lot of work to be done to stage the construction. As they added weight, they had to take weight off. And that was possible because the pontoons have ballast. So they have rocks inside of each of those cells in the pontoons. And so as they add weight from the track and from the railroad ties and from the overhead catenary system that carries power, then they can take some of those rocks out.
Wow.
Yeah.
Literally just adding the track, taking some rocks out of these
Pontoons.
the pontoons.
That's right, yeah. And that allows the bridge to maintain its current, it's called freeboard, but how deep the pontoon sinks into the water.
Okay.
So they wanted to maintain that while they were doing this whole construction.
Because I'm trying to wrap my head around, you're dealing with the weight. You're dealing with moving from water to land. There's an adjustment in the bridge right there. What really makes this work?
The people. And, this project has been going on for, even my involvement's been almost 15 years now. And so to think about the tremendous number of people who have been involved in this project, I've heard this project described as a relay race because it's seen so many different phases. And there's always sort of a passing of the baton on who is responsible for that portion of the project delivery. And so I was fortunate enough to be involved in some of the very early stages on the Track Bridge project. And now to see that come to fruition, it's a totally new cast of characters. And so I think it's just a testament to the tremendous amount of engineering that's gone in to make this project complete. And all of those people working together to solve problems, understanding that things don't always go the way that you'd hope them to go, but there are solutions and that there are things that we can do to make sure this is a successful piece of infrastructure that will hopefully last for generations.
And you have gotten to be part of the first leg of the relay race, and now this final leg.
That's right, yeah. And so one of the things that I'm really excited about now is I'm working with the Mobility Innovation Center here at the University of Washington. And, the work doesn't end here. And I think that's one of the things that's interesting about a project like this. So now we have a bridge we have a train on a floating bridge, first time in the world, and we need that structure to last 100 years. So we're 40 years in. how do we get this bridge to survive another 60 years plus?
Yeah, let alone the tracks. We need the bridge to survive.
That's right. And so...
So what's your department doing?
So we've started a project. It started with WashDOT, so Washington Department of Transportation. Now we're working with Sound Transit to instrument the bridge in addition to the instrumentation that's already there, and to develop a digital twin of the bridge structure. So this is a digital representation of the physical bridge.
So you're going to put sensors all over this thing.
That's right.
Okay.
And so that's all being brought in real time to the folks that are out there, so that everybody can have the same information when they're making decisions about operations and maintenance, because that's going to be a huge portion moving forward, as how do we keep the train operational, how do we keep the bridge operational, and how do we optimize the maintenance of this structure so that we can see another 60 years of operation.
Is this project that now you can point out to your kid and your wife and engineers probably all over the world, is this something that is a feat being celebrated outside of Washington State?
I think, when I mentioned there's a list of a few projects in the 90s that had done similar things, it's going to be one of the projects that people look to. The thing about this project is there was no design on the shelf that people could go and pick up and say, aha, we'll do this again. This was something that we had to start from scratch, had to come up with solutions for all these different issues. And I think now when people have a similar issue, this is going to be, or have a similar design challenge, they're going to look to this project and say, they did X, Y, and Z. So now they do have a design that they can modify or use for that. So that's pretty neat. This is going to be something that people can use in the future.
University of Washington Assistant Professor of Civil and Environmental Engineering, Travis Thonstad, thank you so much for breaking all of this down for us.
No, thank you for having me.
Thank you so much for listening to Seattle Now, and thank you so much to our donors for making this show possible. Another great way to support us is rating and reviewing the show on your podcast app. Today's episode was produced by Brooklyn Jamerson Flowers. It was edited by Caroline Chamberlain Gomez. Our production team also includes Andy Hurst, Vaughn Jones, and Patricia Murphy. Greg Kramer does the theme music. Seattle Now and KUOW Public Radio are members of the NPR network. I'm Paige Browning. See you tonight for Evening Headlines.